Hello, everyone. So my name is Jay Henderson, and I'm here today to present some work I did as part of a research internship at Meta Reality Labs during my PhD. So the work is called Investigating Cross-Modal Approaches for Evaluating Error Acceptability of a Recognition-Based Input Technique. And this work was done by myself, my Meta collaborators, Tanya, Jonker, Wigdor, and Ben Lafreniere, as well as my supervisor, Professor Edward Lank. So despite significant advances in sensing and recognition, systems that incorporate recognition-based input modalities will inevitably make errors. And this is due to imperfect sensing or noisy input. And so when this happens, these systems fail to capture or properly interpret user input. So this then raises the question of what level of accuracy is actually acceptable to users. In addition, accuracy can also be subdivided into precision and recall. So precision is based on how often the recognizer falsely detects an input occurring or a false positive, whereas recall is based on how often the recognizer misses input that you actually did perform or a false negative. And these recognition techniques can be developed to favor either precision or recall, and this is usually based on how detrimental each type of error is. To inform the design of these systems, it's really critical for designers to have an understanding of what the acceptable error characteristics are, so that we can devote resources properly and weigh these things properly for the best user experience. So this means what levels of accuracy, precision, and recall are actually acceptable to users. An example of one of these types of systems is mid-air barehand input for virtual reality. And so this is an emerging input technique that relies on fusing sensors, cameras, AI technology. And so we felt that this was a really good test bed to explore error acceptability. But the problem is when you try to test something like this, due to the nature of the equipment, it can be costly to produce a full kind of simulation. It's difficult to scale as people don't have this equipment readily available, and it's inflexible to re-engineer and retest different applications or contexts. Because of these limitations, in this work, we introduce a spectrum of modalities geared towards eliciting what are acceptable error characteristics in full simulations of emerging input techniques, which in this case was a VR simulation. So the spectrum is on a scale of really lower cost and low fidelity to high cost and high fidelity. So the lowest here on the left is text descriptions, followed by video explanations. But closest to the full simulation is what we refer to as a cross-modal simulation, and in this case is a tablet simulation. And so this would be similar to providing a prototype experience. And we hypothesized that this approach will provide more mechanics similar to the full simulation, while being less costly to test and develop. And so in our work, we first wanted to look at error acceptability using these first three approaches to see where the differences lie across modalities. And we looked at these on two different target applications. The first was a high urgency game where we would expect errors to be more detrimental. And the second was a low urgency painting application where we expect errors to not be quite as problematic. And so this video shows the VR game application that we wish to assess. So the user does this pinch plus directional gesture to control a ball. Occasionally, they will see errors that we artificially inject. So here, the user performed an up gesture, but the system ignored it, which caused a crash. And this is an example of a false negative. Here, we see that the user did not perform a gesture, but the system incorrectly detected a gesture, which also caused a crash. And so this is an example of a false positive. This video here shows the VR Paint application that we wanted to assess. So the user does the exact same kind of pinch plus directional gesture, but this time to select colors and redraw an image. Again, there are errors injected. So here we can see the user performed a left gesture, but the system ignored it. The user can recover by just selecting it again. Here we can see the user did not perform a gesture, but the system did detect an up gesture, which caused a blue selection. And this is an example of a false positive. So like I said previously, we looked at text, video, and a tablet simulation. And so here's what the tablet simulations look like. So most of the interaction mechanics remained exactly the same, but they had to be done while retaining contact with the screen. So in our protocol, we had a within subject study where we tested 3 modalities on 2 applications with 4 different error scenarios. And so we collected Likert scale metrics by adapting K et al.'s 2015 Chi paper, How Good is 85%, and combined it with the NASA TLX to kind of understand really the user experience of seeing errors. And we really wanted to understand the acceptability, the usefulness, the effort, and frustration and overall user experience when the users saw each error distribution in each app on each modality. So here is a set of diverging bar charts from the Likert scale responses. But for the sake of time, I'll just focus in on some of the results. So if we zero in purely on frustration, we can see that the scores are fairly consistent across modalities for the high urgency game. However, if we look at the paint application, participants were much less frustrated from errors when they actually tried the cross-modal tablet version versus the text or video scenarios. If we looked at effort and overall user experience, we also see the same type of pattern. So in study 1, we found significant differences between the interactive cross-modal simulation and the non-interactive approaches, which provides evidence that there are certain aspects that require experience in order to understand how acceptable error distribution is. For the second experiment, we wanted to qualitatively understand which aspects could not be communicated via a cross-modal tablet simulation. So we did this by directly comparing it to the full VR simulation that leveraged actual midair input. We ran the same protocol, but this time on just the 2 modalities, the cross-modal tablet version and the virtual reality version. But this time, as well as the initial questionnaire, we looked at qualitative metrics to specifically probe for differences between the 2 applications and modalities. And so while I can't quite go through all of the results, we did find some interesting themes from our qualitative analysis. The first was that the context of the app mattered across modalities. So participant 1 said that though the gestures and errors felt the same, the canvas interaction felt very different because you weren't actually touching the canvas in VR. It made the Paint app harder to use. Next was comparing the gesture input actually in VR versus on the tablet. And we had 4 participants feel that errors were more obvious on the tablet than in VR, since the nature of touch input is much more explicit and they're always being monitored in VR, so the errors made more sense. Also related to the prior point, we also found that expectations from prior modality experience can influence error perception. So for instance, one of our participants noted that they are used to errors as they use hand tracking in VR, so they were much more forgiving when they saw these errors crop up. And after concluding the 2 experiments, we came up with a list of characteristics related to error rates and whether each modality is capable of eliciting them. So as you can see, text is probably the most capable of communicating the exact error rates, since they're explicitly stated in writing, but text cannot conceptualize the difference between the applications, the context, and the interaction dynamics, such as time. Um, the amount of effort and emotional reaction to errors, such as frustration, can only be communicated in an actual interactive version, such as the Cross-Modal tablet version or full simulation VR version. But lastly, the exact interaction mechanics can only be elicited in the full simulation version. Um, so that concludes my talk today. While I know I glazed over a lot of details, feel free to reach out and if you have any questions, and I encourage you to read the paper if you're interested. Thank you.